All right, so I'm recording now. All right, so for this one, we're going to do every other. So A, C, E, like that. All right, so to remind you, the very first thing of scientific notation is that you have to have a number to the left of the decimal, only one, and it has to be between 1 and 9. And also the direction that you count, and there's somebody. The direction that you count, whether it's right to left or left to right, I don't like that, but I say that if it's larger than 1, then you have a positive exponent. If it's less than 1, then you have a negative 1, okay? So this is what we're doing with this one. We are also, the other thing that is important is to know how many sig figs your original quantity has. Because if you, oh, and by the way, I'm not going to do times 10 to that. I'm just going to do E to the 1, okay? I'm doing E because exponent's easier than me to having to go 10, then go to the little subscript, superscript up here and all that stuff, which is really annoying. All right, so this one right here, the C, example C, you notice we have 6590. But officially, only 6, 5, and 9 are significant, right? So we do 6, 5, 9, but we still count the movement. Oops, sorry. E, I just said I was going to do E and I was doing the other one. E to the -3. I mean, so +3, sorry. All right, so when you're looking at that, you're saying we are moving at 1 and we're moving at 3. Therefore, our exponent shows that. And it was larger than 1, so it's positive. This one, we need every single one of these sig figs. So 1.58212, 8212, okay? And we moved it, let's see, count. 1, 2, 3, 4, 5. So then E to the 5th. And that is that one. I'm putting them in red so you know that these are your answers. And every time I will try to put them in red. All right, this is the only one that we have that is going to be a negative because it's less than 1, right? So it's 5.68. That part doesn't change. Now the E is still the same amount of movements that it took to get to it. So 1, 2, 3. And remember, I gave you a tip that if you're looking at a negative number or a negative exponent, always count the number of zeros that you have and then add 1, and that gives you the exponent. So like the top one would be 4 right now, right? So it would be -5. All right, now as far as the other ones, not so much. The positive ones, you can't generalize anything because there's no rhyme or reason to it necessarily, except that you move however many spaces you need to move, and that's it. All right, again, this one only needs these 4 sig figs, 5, 6, right? But we still need to count how many we moved. So 1, 2, 3, 4, 5, 6. So this is E to the 6. And that is how you do scientific notation. If you recall, that's great. If you didn't, now you know. All right, so the next part, we're going to do the opposite. So to do the opposite, all you have to do is reverse the process. So notice this -7. So I don't know why it does this. All right, so let's do 0.12345 Remember I told you it's 1 more than the amount of zeros. So in this case, 1 less 0 than the amount of numbers. All right, 6.3. Then the number it's upstairs, I should say. Sorry, not the amount of numbers. I don't know why I said that. I'm going to move these over so that we have enough room for them. Okay, there we go. All right, so that is our, again, we're doing only every other. So this one right here is going to be, all right, this is -4. So again, 3 zeros, 1, 2, 3, and then 5, 6. That's how you do those. You just go with what it tells you to do and add the 0 accordingly. All right, this one is going to be a positive. You notice that is a positive direction, which means that your number that you should have had is, okay, wait, that is not working. It's more than 1. So you're going to move it 2 times. So it's 756.8. That's how you started with this one. The next one, which is G, right? G is going to be to the 9th. So 2 point that, oh, there's no point. So that's 1, 2, 3, right? Oh, sorry, 1. Okay, that's 3, 4, 5, 6, 7, 8, 9. And there you go. That's how you do that one. The next one we have, oh, and let me color it red so you know that that's our answer. This one is a negative, and it's only moving 1, so it's 0.85. And that's all of them, right? That we're doing. I mean, the rest you can do yourselves, and you can turn them in for extra credit. And again, this extra credit goes directly to your final, which means that you're going to have 25 points that you can earn towards your final, which is 200 points. Okay? All right. So carry out
Yes,
the, oh, I'm sorry.
I say yes, ma'am.
Oh, okay. Sorry. All right. So the conversions, I like to do them in the way that I showed you guys, which is using the dimensional analysis. So we're going to use that. And for that, I'm going to have to insert a table, which is what I used to kind of do. Now, we may not need this much, but we don't know. So we're just going to use this number, right, that we're here. I'm going to put it here because that's where we're starting with. And we're going to centimeter cube. So 1 liter of, first of all, well, no, let's do 1 liter to milliliters. Why do we change to milliliters? Not because we can, but because we need to. We actually need to change to milliliters because 1 milliliter equals 1 centimeter cubed. So we want to change it to milliliters. Okay, so what would this be? Remember, this is, we're going up. No, we're going down, right? So we're going from liters to milliliters, 3 spaces. So we write a 3. And that is milliliters. Sorry, I forgot to put the units. And then 1 milliliter. And if you want to do the whole full conversion, you can. I mean, it's not necessary, as you know, because, well, 1 to 1, right? So, but I'm just going to do it so that you see it. 1 milliliter is equal to 1. Why is it doing this? This is annoying me. I have to change the number every time. 1. And I'm just going to copy this guy so I don't have to retype him. Centimeter cube. And see, that's going to give you the answer in the right units. So basically, you're just multiplying 8.79 times 10 to the negative 4 times 1 times 10 to the third, which, if you recall from our previous learning, we had to add the exponents. So if we add them, it's just going to be 8.79 times 10 to, I'm just going to copy this because it's easier. Times 10 to the negative 1 this time, though, because we're subtracting, and that would be milliliters. And that's it. Oh, sorry, centimeter cube, not milliliters. Milliliters would be what I would leave it as, but that's just me. Don't be lazy. Don't be lazy like me. That is not what you want to do. All right, and there's your answer. So I'm going to make it in red so you know that that's the answer. Okay, and there you go. So you notice that your liters are going to cancel out, your milliliters are going to cancel out, and you're going to end up with centimeter cubed. All right, we're doing B next. No, not B. C. Sorry, C. C, we're doing the same thing. We're inserting another one. I think a 4 will be. If we don't use it, we don't use it. That's fine. Okay, so 117 milligrams, right? To grams. So again, milligrams needs to go on the bottom and grams goes on the top. We're going up. So this is 1 times 10 to the negative 3. And that is grams. Oops, sorry, not pages. 1 times 10, 1 times 10 to the negative 3 grams. Okay, so that's it. We don't really even need this amount. We just need that ending. Okay, so basically, actually, we did need it, don't we? Well, we can put it on the bottom. 1.17 e to the negative 3. But remember what we've said about that. We need to move it 1, 2. So we're decreasing it by 2. So we increase this one by 2. So then our answer is actually 1.17 e to the negative 1. Every time I say e, I put a 3. I don't know why. All right, so this is actual answer right here, the only one that's in red, and that is grams, right? Okay, and that's that. So that's how we do our conversions. The next one that we're doing is E. E is, again, we're going to just insert the same table, even if we don't need as many as 4. Oh, why are you not letting me insert a table? Oh, okay, I see why. All right, table of 4. There we go. All right, so the very first thing that we know is this, and we know we're changing it to meter cube. So that's one of the things that a lot of people get confused with. We know that our conversions are not in cube, right? So we need to cube them. And that's the thing that a lot of people get confused with. So this is going to be cubed. And sorry. Ugh, there goes my first of 400 calls. Oh, I get so many, it's ridiculous. Okay, this should be 11, not 12. Okay, so this one is going to be 1. Oh, and we need parentheses again. 1 e to the negative 3, right? Because we want to go to meters. I'm sorry, negative 2 meters. And then we do the squaring. I know I cubed it. I just realized that. No, it is cubed. It is cubed. I squared it in the wrong one, didn't I? It's cubed. Sorry. There you go. Okay, so there, once you multiply, divide, you know, you're going to get 1. By the way, when you elevate a number with an exponent to a third power, you have to multiply it. So the 2 powers. So that is like saying 101.3 e to the negative 6. And that would be meter cube, right? Okay, so again, that is incorrect scientific notation. So we need to change that. To change that, that would be, we're moving it. How many spots? We're moving it 1, 2 back. Since we're moving back, we need to increase it by 2, right? So plus 2, right?
Yeah.
So that's going to give us 1.013 e to the negative 4 meters square cube. I keep saying square. I don't know, I have a square in the brain. Not, I don't know why, but I do. All right, so that is our answer right there. Official answer, last answer, the end. Okay.
Yes, ma'am.
All right. Decrease, increase. Remember that little tidbit that I gave you guys. Didn't really need that, so we just took. All right, next one that we're doing is G, right? EFG, yeah. So G, I'm going to insert it right here. It's going to be weird because it's going to be like in a weird spot, but you'll know which one it is based on the fact that I am putting the same numbers that are on there in here. All right, so G is 2.5 liters. So 2.5 liters to milliliters. This one's very straightforward. 1 liter is equal to 1 e to the negative, no, to the positive 3, because we're going to milliliters. All right, so remember, we're going down, so it's a positive exponent. The answer to this is just simply 2.5 e to the third milliliters. Oops, remember I said every time I hit E, I hit the wrong number there. All right, there you go. That's our answer and the end of this. All right. And do we have any more? E, F, G, H, I. Do we have an I? Yep, we do. All right, so let's do I. I is, we're going from milliliters to liters, so it's the opposite. I know already I'm only going to need 3. So we're starting with 5.36 milliliters, right? And I always like to put the milliliters on the bottom. And so since they are on the bottom, we're going up, you know that is going to be a negative exponent.
Mm-hmm.
And when you multiply it, you just end up with negative instead of positive. That's it. 5.36 e to the negative 3 liters. And there you go. And if you were to want it in actual numbers, that would be 0.0536, right? Liters. But I'm not going to change that. I'm just letting you know that. Okay, so that's all of those, I believe, so far. All right, yeah. All right, so as far as sig figs, remember the sig figs matter because of precision of measurement. So 3 sig figs on this one. This next one, oh, and by the way, people are people. You cannot half them. Therefore, that would be unlimited or infinite or whatever. This is a conversion. So I'm going to say unlimited, but it's actually limited. And how about just put limited by the number converted as that, because that's the problem. Is if you have a conversion that is just like this one,
Mm-hmm.
this is all this is a conversion factor. They do not bring any sig figs at all.
Right.
What brings it is what you put in front of it, like we did up here. You notice that we didn't have more than 4 sig figs on that answer, right?
Yes, ma'am.
So that's what I'm saying by limited to the number being converted. So, all right. So DE next. Okay. You notice this is 60.00 milliliters. So yes,
It's 600.0.
600, right? Sorry, I meant to say 600. I'm speaking and I'm saying other things, but my brain is saying the right thing. It's just I'm having disconnection today. But that makes it 4, right? 4,
Yeah.
because we include, since we do have a decimal right there, we
Mm-hmm.
include that 0 also in this one. I'm just going to put that on there. So you know that that's an actual answer. Okay, E, F, G. This one, it has no decimal. There's only 2. Remember
Yeah.
that.
Mm-hmm.
I think you guys haven't forgotten that one yet, but maybe you have. And if you did, then this one's also 2, right?
Yes, ma'am.
Because even though it has a lot of zeros in front, they don't count. They're just
Right.
places. Okay, so I did all of those. A, B, C, D, E, F, G, H, O, H, I. Oop, I skipped I. I is only 1. Why is it only 1? Because we do not count the zeros when there's no decimals. Okay. H. Okay, so we should have done H too. H is actually, no, no, H we don't need, but you always look at this number, never at the other part. So you know that that's 4. Okay, so let's keep going. Now we have conversions in temperature. So for these, I'm going to do A, C, E, and F. All right, so A, the first one we're doing is 2 Celsius. So we use the C formula, which states that you have to subtract, right, 32 from that and divide it by 1.8, 1.8, not 118, 1.8, not comma, dang it. My fingers, they're having disconnection too. I'm all disconnected today. Okay, so that's going to give you 115 minus 32 divided by 1.8 is equal to, no way in the world that's right. What did I do? I don't know. Let me see. Maybe I didn't clear everything. I was like, that can't be right. 115 minus 32, that gave me 83, divided by 1.8. That is 4.6. That doesn't sound right either. Oh, 46. Yeah, that's more like it. I was like, wait, 46.1 Celsius. There you go. There's your answer, which makes sense. You had 3 sig figs. Usually I don't like sig figs with temperature because it can be very dangerous to put sig figs on temperature. So what I'm doing with it is I am actually just giving you 1 decimal. All right, now we're going to Fahrenheit. So the F formula states that you need to multiply your 19 in this case, right? Your Fahrenheit times 1.8, then add 32. Notice that all the same numbers are included. They're just totally different. So 1.8 times 19 plus 32, I got 66.2. Is that what you get?
Yes.
Being that I'm disconnected today, you better be checking. All right, there we go. All right, so next one is E, A, B, C, D. Yeah, E. I'm gonna move him down. It's just, it looks weird there. All right, so Celsius. Okay, this one's easy. All you gotta do is add the number that's on there plus 273. Actually, to get to Celsius, to get to Kelvin. So the reverse is true from this one if you want to get to Kelvin. So just subtract 273 to get to Celsius. So we get 598 minus, dang it, I keep pushing. I told you I'm disconnected today. I don't know. Or my fingers want to do the right thing. That is 325 Celsius. I don't know. It is just weird. Okay, and then the last one is my Kelvin. Okay, we want Fahrenheit to Kelvin, and we know that there is no direct connection. So we need to convert to Celsius first. So remember, 23 minus 32, yes, this is a negative number, divided by 1.8. And then, there's the period, 1.8. And then you add 273 to the answer, right? And that'll give you your Kelvin. All right, so basically we're just 23 minus 32, that is 9. And then plus 32, right? That gives me my Celsius. No. Oh, no, 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 no. See, you
Yeah.
didn't say anything. That is so wrong. It should be minus 32 divided by 1.8 because we're going the opposite way. Yeah, we're going two. Oh, stop it. I keep hitting the period instead of the comma instead of the period. Okay, there we go. That is so not the right answer. Wait, what did I do? Oh my God.
That's the wrong formula because that one
Yes,
is
I
Celsius to
know. I
Fahrenheit.
changed the wrong one. Told you I'm this. I don't know what is wrong with me today. Oh my God, what is wrong with the professor today? She is crazy. Okay, that was correct. Plus 32. This was correct. This bottom that is that is correct also. I don't know what happened when I did that. 23 minus 32 gave me negative 9, right?
Mm-hmm.
Divided, no, not divided in this case. Yeah, divided by 1.8 gave me 5, negative 5. Then we add 273 to it and you get 268. That one is correct.
And on C, you put 1.80 instead of 1.8 parentheses.
I don't do the 115 thing. Oh, yeah, the parentheses. I know. That was supposed to be a parentheses. I just didn't hit it hard enough to go shift. I guess that's what happened because that's what it is. When you don't shift up, the parentheses are right there with the 0. All right, so there you go. So sorry about all those crazy things, but you get the formulas, right? They're right there. So the Fahrenheit formula, when you go into Celsius, you're going to do the Fahrenheit minus 32 divided by 1.8. When you're going to Fahrenheit, you're going to do the Celsius times 1.8 plus 32 at the end, and then the other ones you see. Okay, so all right, so the next one is a density kind of conversion problem. Yes, density. Oh, excuse me, now I got the yawns. Density can be used to convert anything. Now, you notice they're telling us that this is the question right here, right? This is the volume of the gold bar. So, but they gave us the measurements, not the answer. So, whatever that's going to be, that's what you're going to do to convert. That's going to be in centimeter cube, right? So that ends up being 300, right? I'm just showing you where that came from, just in case. Oops, centimeter cube. All right, there you go. So that is the one that we're using, this one. I'm just highlighting it so you see which one. Okay, so now we want to know, first of all, the mass of gold so we can convert it to volume of water. All right, so the mass of gold is 19.3 grams for every cubic centimeter, right? See? And now, and I'm going to use the next one. I'm going to use this one in blue. So I'm going to change it to blue so that you understand that I'm actually using the units for water. So this was gold, right? Now I'm using the water. So for this one is 1.00 grams for every 1 cubic centimeter of water. And yes, I know I haven't changed it yet, but I'm going to. There. All right. So all you got to do is multiply 300 times 19.3, and you got your answer. And watch your sig figs. And that is 5.79 times 10 to the third, but we can only keep one sig fig, E3, okay? And that would be centimeter cube of water, right? But sig figs, it says 6 times 10 to the third, E3, yeah, centimeter cube. Why does it do that? Because we only have one sig fig here, right? And we really ended up with just one sig fig in our answer too, look. So one sig fig dictates how many we have. So the actual answer is this one, which would be 6,000. And remember, I'm putting the answers in red, so, okay. All right, now the next one is how many seconds are there in a leap year? This one's gonna take quite a bit of conversion. I'm gonna put a 5. All right, so leap year, as you know, there are 366 days, yes? in 1 leap year? Or is it less? I always get that one backwards. Is it more or less? There's more, right? Yeah, because February has an extra day in a leap year. I'm calling it LY. That's okay. All right, the next thing is to convert days, right? So 1 day is equal to 24 hours. 1 hour equals to 60 minutes. Let's not jump the gun there. 1 minute equals to 60 seconds, and that is correct. Now, all you have to do is multiply the top, and that's it. And you're gonna end up with a lot of number, a big number. And you can put it in scientific notation with 3 sig figs because 366 has 3 sig figs. So 3.16 e to the 7th seconds, right? Per leap year, which is what they asked for. See? That is a conversion problem. The next one is also a conversion problem, which I call a study in uselessness, and you will see why in a minute. But we're going to do it either way. All right, so for this one, we have this number that we need to change to grams per liter. So I'm just going to write it right here. And that milligrams per milliliter just means that in this many milliliters, in 1 milliliter, you have that many milligrams. All right, so now you need to change milligrams. So 1 milligram is equal to 1 times 10 to the negative 3 grams, right? So remember, we're going to grams, so we're going up, so it's negative. And then milliliters, we want to change to liters. So 1 liter, right? No, 1 e to the 3, right, is in liters because we're moving from negative 3. Sorry, did I say 3? No, we are moving from milliliters to liters. So we need milliliters on top. And that is for milliliter, for 1 liter. All right, so as you can see, these two are going to cancel. And you're going to end up with the same answer, which is why I said it's a study in uselessness, because grams per liter is the same as grams per milliliter. But that just proved it for you. Okay. Now I'm going to also do 10 because I want you to see an actual double-sided problem like this one. So I'm going to go ahead and insert a table of 4, I think would probably be enough. Okay, so we got 115 kilometers in 1 hour. Yes, that's how much it travels. All right, so for every kilometer, and they want it in meters per second, we have 1 e to the 3 meters, yes? Now you notice that hours also needs to be canceling. So 1 hour is equal to 60 minutes, right? And 1 minute. And since we start on the bottom, we want to make sure that our seconds stay on the bottom, okay? So now you just multiply 115 times, not 15, 115, and then times 1 e to the third, third, sorry, I'm looking at the wrong thing here. And then equals to that, and then divided by 60, put parentheses, divided 60 times 60. And the answer is 3.19 times 10 to the 1. So the answer, I'm just going to put it right here. So 3.19 e to the 1 meters per second, or you can also, it depends on how it comes on your question, right? It could be like this, or it could be like this. As long as you know how to convert it, you're good. See? That's the answer for that one. All right, for these, we need to, and by the way, this is supposed to be decimeter. Well, I'm only doing the first two anyway, but that is supposed to be decimeter, just so you know, so you don't get confused when you do it, because you will if you don't. Okay, so we're going to insert a table again. And the reason I'm inserting a table is, again, you notice that we're going from square to square. So 1 meter squared is not going to be the same as 1 meter ever. So you got to make sure that you square the conversion. We want to go to millimeters. So you know that for every 1 meter, oops, you have 1 times 10 to the third, right? Oh, and don't forget to put millimeters inside too. So square it. So then the answer, it's simply, oops, we don't need this many. The answer is simply 1 e to the third millimeter cubed. No, not e to the third. Why not? Because we're multiplying those two. So e to the 6. And it's positive, yes? So millimeter squared. See that? That's why it became 6. That's why I said it's not the same to change 1 meter to a millimeter than to change 1 millimeter squared to a millimeter squared. Never. All right, so then the next one is C, and we are doing the same thing. We are inserting a table of 3. I know I don't need but 3 now. All right, oh, and I said I would give you the highlighted answer. Okay, so this one we're going from millimeters to centimeters. So millimeter squared. So we know that 1 millimeter, and don't forget we need to square it. So we need to put it in parentheses and square it. Now, that looks like times 2, but I'm really squaring it. I'm not going to take all of that time just to do that. Okay, so millimeter to centimeter, there's 1 space, right? And we're going backwards, so going up. So -1. And then we're, centimeters, and then squaring that. So then the answer is simply 1 e to the -2 centimeter squared. You see that? Again, it is what happens. It changes because it is pretty much doubled. The distance between one and the other is doubled because it's cubed. All right. These are some good ones for nursing students. As a matter of fact, we start with what they give us, right? So first thing to do is insert a table. I'm going to insert a 4 table. I don't know how many I'll need. If I need more, I add more. All right, so it says, oops, I cut it off. Control X. I'm just going to put it up here so it doesn't look so weird. Okay, there we go. All right, you notice that they want us to know in 30 days, which is 1 month, according to them, right? All right, so that's the first thing. Now we have to look at our questions to see if there's anything that has a day. And it does. You see that? Right there. And that is what your doctor is going to tell you one day. We want to know what her maximum supply, the 1 month supply is, because you're dispensing, right? You're dispensing a 1 month supply. So you need to know how many milligrams you're going to dispense, because there may be a limit or whatever, okay? So you notice that for every day, right, she can only take, or he can only take 125, and I'm going to put mcgs, micrograms, right? That's, and it says per day. So, and that is per tablet. So I'm just going to call it tablet. 1 tablet contains that much. Now, they want to know how many because days we already have. So how many milligrams are there? So now we need to convert. 1 microgram converts to 1 e to the, okay, so micro is -6, and milli, which is what they want, is -3. So remember, we subtract those two, we get 3. And then from that, we have to figure out if we're going up or down, and we're going up, so it is -3, right? So when you are doing that, that is milligrams. You're going to get milligrams per month, which is what you want. So you know you've done it correct, is that's what you get, the answer that they're asking for. All right, so the answer is, let's see, clear. We got 30 times 125 times 1 EE -3. And the answer is, oops, oh Lord, I don't know what I did there, but I didn't do it right. 30 times, there goes my disconnect again, times 1 second EE -3. There we go. That now it looks right. I get 3.75, sorry, not 375, 3.75. There's your answer, 3.75, and that would be milligrams per month. You see that? That is exactly what they asked us for. We got the right answer. All right. Now let's do this other one, because these are more important for you guys than the other stuff. I just want to make sure that you had some exposure to what it could look like if you ever did this. All right, so, all right, notice that they're asking us how many grams of codeine per day. And they're telling us that 30 milligram per tablet. So that's what we're starting with, 30 milligrams for 1 tablet, and I'm gonna call it a tab. All right, so the package directions recommend no more than 8 tablets per day. So 8 tablets. And I'm gonna call it per day, even though they say 24-hour period, because we want the answer per day. We don't want it per hour. If we put 24 hours on the bottom, then we would be doing per hour, and we don't want per hour. All right, so that's it. That's all we needed, right? It's, oh no, milligrams. Oh, no, not yet. Milligrams, we need to change to grams. So we're going up. So it is e to the -3 grams. Oops. See, I told you every time I want to hit E, it's the wrong one. Okay, there we go. All right, now we have the right answer. So that would be 330, not 300, times 8 times 1 second E -3. I get 0.24. What did you guys get? 0.2.
0.24 grams.
That's what I got. So the answer is 0.24 grams maximum per day. So per day, right? And we have days still left over. So that is exactly what they asked us for. That is exactly what we gave them. You see that? If you notice that the milligrams cancel out with these milligrams, the tablet cancels out with the other tablet, and then the day is left over. So you got grams per day. Okay, so these are easy. Obviously, that's a solid. That's another solid. What is this one? Clouds in the sky. Well, that would be a gas, right?
Yeah.
And then air is another gas.
Yes.
And then hydrogen in the sun is actually plasma. And then
You said plasma?
plasma. And vegetable oil is liquid. Yeah. We have 4 states of matter that we went over. And the one thing that I remember telling you is that hydrogen in the sun or anything in the sun is going to be plasma because
Okay.
plasma is what the sun is made of.
Right.
Okay. It actually is a conversion of hydrogen to helium because the sun happens to be our biggest fusion generator. All right, so classify each of the following as either chemical change or a physical change. All right, so we're going to do all of these. Electrolysis of water, that means it's breaking it up, so that's a chemical. The formation of fog, okay, sorry. Separation of alcohol and water is a physical. Formation of fog, all it is just condensing, so it's physical. Burning of wood, that's a totally different story, right? Rusting of iron is also chemical. And sand to glass, all you're doing is melting, so it's a physical. So there you go. I'm not putting those in red. You can kind of see that that's not part of the word, right? All right,
Yes.
so draw. Okay, for this graph, you don't have to draw it. I'm going to show you where it is. Basically, you go to your matter. And on here, you have a graph. And you just copy and paste. Oops, I just passed it. You just copy and paste that one. And it's actually this one. No, actually, it's the diagram. Yeah. And in order to do that, I tried doing it earlier, but I couldn't do it because I think I have to download it and blah, 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 which I don't have all the time in the world to do all that. But you could download it right here. See, and then just paste it in there. Save it. I guess I can do that. It was not that long. It was not that long this time. The last time I think it's because my internet was kind of slow. And you just insert it here. So you're inserting a file. It might be a picture. I don't know. Let's find out. I don't think it's, no, I think it's a file.
It's gonna be a file.
Yeah, it's going to be a file. But see, that's what happens with that. Okay, so this is what I was saying. I don't have time in the world for this. It is somewhere in here. It got saved right there. There it is. But see, now it didn't insert. So like I said, you just insert it like that. Okay, so now you know what to do. For
You
some
can
reason,
also probably take a screenshot,
yeah, you
and
can
then
do
like if
that
you
too.
screenshot it, you can just paste the picture instead of a file.
Exactly. There you go. That works too. That works too. Yeah, don't save them. Okay, so, oh, I don't want to save you. I just killed the one, didn't I? Oh my God. Told you I'm disconnected today. I don't know why in the world is going on. Okay. Yep. I'm disconnected here too. Nobody knows me. I was showing Alyssa that when I first looked at that I cannot get into my Canvas account. So I can't work on it. Oh boy. Okay, so back to
Will it take you back if you hit the back arrow on the one with the?
I don't know. I could try. Let's see, with the QuickTime. Come here. Let's see. Maybe it'll take me back to the matter. Yeah,
Oh,
not to where I need to go. No, I remember I totally killed it. But I think I have it still saved up here. Yeah, there we go. I do have it saved. Well, not saved. I didn't save the changes, so you don't have any more of the answers, but you've seen them, and we are recording, so that's okay. All right, so boom, boom. Okay. Yeah, okay. So for each of the following, right, if it's a mixture solution or a compound, we'll go even further, but okay, that's a solution, which is a homogeneous, right? This is a compound. This is a heterogeneous mixture colloid, so it is a mixture. Muddy water is a mixture also because it is a heterogeneous solution, and it is a suspension. Baking soda is a compound. Pizza is a delicious mixture, and bronze is a solution. And there you go. That's all of them. All right, now defining that part you can do. I'm not going to define them for you. You can just go look for them. Now, this one, I'm going to add one more because for some crazy reason, every time I do this, I think about it and then I forget about it and then I forget to add it. And so I'm going to add it now. And that is a plasma. And of course, now the rankings are going to be 1 to 4. So I'm not going to change all of them, but you get the point. All right, so temperature-wise, the lowest temperature is going to be a solid because, you know, think of ice, right? Ice is cold. Water is kind of not so cold, right? Gas is warm, very hot. As a matter of fact, it'll burn you if you are doing water, so it is steam. And then in the sun, it would triple burn you. So yeah. So, you know, sorry, I meant to say 2 here. What did
It
I?
says 1 is the lowest
Yeah. Oh,
backwards.
I'm backwards. See, disconnect again. Oh, Lordy. Okay, so 1. Yep, you're right. Thank you for that. 2, 3, 4. If you see me do something again disconnected like that, it is what it is. I'm just disconnected today. All right, so kinetic energy, as you know, is a function of temperature, basically. Temperature is a function of kinetic energy. I should say it's a measure of the kinetic energy in a system, right? So, and you cannot move if you don't have space. So obviously that's also like that. However, in order to stay close, you need forces that attract you, right? So it's backwards. You see that? All right, this one we're going to look at the periodic table and just remember the trends that like we used to. All right, so for this one, we have the trend, which is atomic radius increases to the left and down. So looking at both of those, you can see that bismuth is lower than phosphorus, right? So I'm just going to change its color and make it be the answer to that question. Remember, red is the answer. So I'm doing that with this one. All right. And then rubidium or antimony. Let's see, antimony, it's way over here on the right. Rubidium's on the left. So rubidium, right? Okay, now let's clear that one because that is no longer that one. As far as radius go, atomic radius, ionic radius, when you are making a positive ion, remember you have to lose one of your electron levels, therefore you're going to get smaller. So the ion is not the biggest in this one. But in this case, with selenium, you are gaining 2 extra ions. So you're imbalancing all that beautiful balance that you had of charges. And of course, the radius is going to get bigger. All right, as far as electronegativity, we need to, let me change the color because that's hard to see. We're going to go to the right and up. So it's exactly backwards from the other one, right? So it's selenium or gallium, not sure, let's check. Selenium is to the right of gallium. So selenium would be the right answer, right? And then chlorine is above astatine, so chlorine would be the right answer. You notice that these are exactly backwards from the other ones. Affinity, electron affinity, again, same thing. Same trend, except this time we're including the noble gases in them. So is it yttrium or technetium? Technetium is more to the right, so we are going to assume, and remember, we don't want to look it up. We just want to use our knowledge of this trend. All right, and then the last one is a helium or radon. Helium is much higher than radon, so it's helium. And there you go. And notice it says why. All you have to do is explain that as you know, an atom gets bigger as you go to the left and down. So that's all. That's all you need to say for that. All right, now we're going to do a beautiful table that you guys love to do, don't you? They're like not saying anything. All right, so for this one, remember, every time that you see a symbol like this one, you are also going to have the atomic number below, but I omitted it so that you would look for it because we need to look for it. Okay, so the atomic radius for, the atomic number for potassium happens to be 19. And as you know, the protons are also 19 because those two are the same. The mass number was given to us as 39. The neutrons is a subtraction of the mass minus the protons, which is 20. And the electrons, since we have a positive one, it means we lost one, so it's 18. Calcium is 20. It's right next to potassium. Obviously, the protons are 20 also. The mass is going to be 21. The neutrons is going to be, oh, sorry. Did I say 21? See there, I disconnected again. 41. The neutrons is going to be 21. And the electrons, no change because we don't have it charged. The next one is gallium. Gallium, where are you? You are 30. No, that's germanium. Gallium is 31. 31, so the protons is also 31. The mass that they gave us is 69, which means our neutrons is 38. And our electrons, we lost 3. Therefore, we have 28, yes? Not that disconnected as far as the math goes. 17 is our chlorine, our atomic number, so that means our protons are 17. They gave us the mass as 37. It means we have 20 neutrons, and we have a negative charge, which means we have gained 1, so we have 18 electrons. Oxygen normally is 8, right? Atomic number, which is the protons. They gave us a mass of 18, which means we have 10 neutrons and same number of electrons as protons because we have no charge. Uranium is 92. That means we have 92 protons. The mass is 235. Is that 143? Yeah, I think, nope. Yeah, 143. Yep, okay, and then we lost 4 electrons from 92, so that means we have 88. All right, and that's that. That's the whole table. Any questions? No? Okay. All right, this one, remember this one, all you have to do is take the mass that they gave you for that silver, multiply it times the percent abundance they gave you, but divided by 100, so not in percent, so 51.8, right? And then add it to the same thing for 109. And if you put it in your calculator like I just did, you will do it much faster. So clear that. It's 107 times 5, 18. plus 109 times 482. And I get 107.964, which says to do it to 3 decimal. So 964, right? All right, and there you go. That is how you do that one. All right, long and short. Okay, so I'm going to do A, C, and E. And I'm going to do the long, short electron configuration here. So 1 S2, 2 S2, 2 P6, 3 S2, 3. Okay, so remember, you have to follow the periodic table. And the 1 is just merely telling you where each one of those electrons is in level 1, and that there's 2 electrons, and that they all are s orbitals. The 2 is telling you you're in level 2, and you have 2 types of orbitals, s and p. So they're both full because you achieved, if you add both of those together, 6 and 2 give you 8. And that is all you needed there. Whereas the next one, the 3s is also level 3, and the s part is full, but the p part is not. And remember, if you add the 2 plus the 3, it tells you that you are in group 5A, which you are. And the 3 in front of the 3S and the 3P tells you that you're in period 3, which you are. So that's a really good thing to know. Now, as far as the shortcut configuration, you substitute the closest noble gas, and by closest, I mean without going over, kind of like Vanna White, for the poor electrons, which in this case is neon, right? And then you just use the rest of the configuration on it. And that's what that is. I'm not doing the other part just yet. I'm going to do it all at once because I don't have to write it 4 times this way, if you're okay with that. All right, the next one we're doing is argon. So argon is going to be 1s2, 2s2, 2p3, 3s2, and 3p6. Because it is in group 9, we are going to be full, and we're also a noble gas. So that is what that is telling us. And our shortcut configuration is very much like the one for phosphorus, except on the back you have 3p6, which is what I'm doing. I'm just copying it. All right. Now, sulfide ion, in this case, is going to be a little different from the others, right? Because we have a number of atoms of electrons that are already in there for sulfur. And we are also adding 2 more. So let's put that in. And in this case, for sulfur atom, right, which is in group 6, we would have 4 there. That's the sulfur. But we are adding 2 more. So we actually have 6 here, which now if you look up at the argon, it looks just like it. But I'm going to put that last 6 in red only because it symbolizes that there's something different there, okay, than what it should be. So that means that you're an ion and you added extra electrons. All right, so those are my 3. Now for the phosphorus, I'm going to draw this, so bear with me. 1, 2, 1, 2, 3, 1, 1, 2, 3. Okay, so this is our phosphorus item. The first level, which is 1s, right, is going to be full. It has 2. Remember, 1s, the s can only hold 2. The 2s is also full because it only holds 2 also. And no, they're not bigger electrons. That's just my hand moving weird because I'm having to do this with my mouse, and it is not the prettiest thing in the world. The 2p electrons are also going to be in there. And if you notice, that whole entire level of electrons is completely full. So therefore, these are your core electrons. That's what's symbolized over here in the neon. Then you have your valence electrons, which are the ones on the outer shell. And for phosphorus, you have your 3s, which is completely full. And then you have your 3p, which is not full. You actually only have 3 electrons. And the way that we fill them into orbitals is we must put 1 in each one of our orbitals, which are represented by these dashes, by the way, or these whatever lines, whatever you want to call it, first. And that is it. We're done with phosphorus. So this is phosphorus right here. So if you want to write it in, because I'm going to destroy it here in a minute. So that's phosphorus, okay? Now, if we are doing argon, we need 3 more. So now the Hund's rule allows us to put doubles. Oops, that is an ugly one. Okay, because now we are full. So this one is no longer phosphorus. It is now, come on, argon, right? Okay, so this configuration is for argon, right? But we also need to do sulfur, sulfide ion actually. So I'm going to erase those few that I made last and change them color, just so that you understand that some of these came from somewhere else. So then this one is sulfide ion. Hold on, I need to erase that P. All right, so this one is sulfide ion. And those 2 extra electrons are what makes the negative. You see? And that's how you do orbital diagrams. So we did all of that. We did long, short, and the orbital diagrams. And if it came back to you, that's good, because that is what we aim to do, is for it to be a refresher, right? So we want that. Okay, oops, I need to change that because otherwise it'll just keep on traveling with me. All right, according to this, it says name one trend among each of the following families. So I would say for alkali metals, I'm going to use, what am I going to use here? Let's use size. So atomic radius increases going, and you notice this is just a period, right? So we're just doing this particular period going down, right? The period. And left, obviously, but we just want this answer, right? The next one, alkaline earth metals, we're going to use electron affinity or ionization. Let's use ionization energy. Ionization energy. Okay. So ionization energy increases as we go down, go up, in this case, not down, the period. No, the group. I put period both times, didn't I? I meant group. Oops. Group, 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 group. All right, okay. And then we can make, let's see, it takes more energy to remove second and third electrons, right? Then first. Okay, how's that? That way we know, right? That's the ionization energy. So it takes more energy. So halogens, we're going to do the one thing that they're very famous for, which is electronegativity. Increases. Energy. What happened to my E? Okay. Increases as we go down the group. No, as we go up the group, sorry, up the group, not down. This is backwards. Fluorine is the most electronegative element. That's why I chose it. You could say that. All right. And then noble gases, I'm going to use electron affinity with them because they do want to hold on to their electrons, right? So increases going up the period. And you can say the less electrons an atom has, the harder it is to remove it. Okay, harder.
Supposed to be going up the group.
Yeah, I said period, and I said group, didn't I? But I said period. I wrote period. What is it with me today? Okay, so no, we don't want that. We want period. Okay. Dang. All right. So now that you know that, think about this. If a noble gas could form a positive ion, which of the noble gases would form it most easily? Based on my answer to D, the part D to noble gases, that has to be radon, right? Because radon has the most, right? Radon it is because it has the most electrons of all. And we said that less electrons an atom has, the harder it is to remove them. Well, this one has a ton, so it must be easier. All right, as far as electrons, how does an ionic bond differ from a covalent bond? And you can say an ionic bond is a sharing, no,
No, ionic
transfer,
loses or gains.
transfer of electrons, yeah, from a metal to a non-metal. Remember that? And then we can just, a covalent bond, thank you, is a sharing of electrons between two non-metals.
You wrote electrons twice.
Electrons, I think it did that for me. I said yes, and I'd already wrote it, I guess, so I just rewrote it. Okay, there you go. Does that make sense? So you are totally different because one is a total transfer and it's between two different elements, two different type of elements than a covalent, which is a sharing. All right, now ionic covalent, nonpolar covalent. Okay, there are two ways to tell. The first one is electronegativity difference. So electronegativity difference, and where is my delta? I just want to insert a delta in there. Symbol delta. There we go. Delta En. Okay, so in this case, since it is a ionic one, when you look up, and I gave you guys a sheet with the electronegativities, that was on purpose, so that you would have it for this particular reason. You should be able to find it in your naming compounds packet. If I can find it, that'd be nice. Okay, where are you? Thing. I have it in here, I just can't find it. I am not seeing it. Okay, so much for that one. I thought I had it right here. There's all of my stuff except that one thing. And I have everything but that. Okay, but I do have a copy, so I got it. All right, so according to this graph that I gave you guys, it's like a pie graph, bar graph, sorry, not a pie graph, a bar graph. All right, sodium has an electronegativity of 0.9 and the chloride has 3.0. That gives me, oops, that was supposed to be a negative. 0.9. Okay, so delta electronegativity just means subtraction, right? That gives me a 2.1, yes? Okay, so that's one. I'm gonna do the delta electronegativity below this one on the other one because it'll be easier to do that. Okay, so NO2. Let's just go to it. All right, Control V. All right, so nitrogen is 3 and oxygen is 3.5. 3.5 minus 3, right? That is equal to 0.5. And then aluminum, I'm going to go across all the way down there and put it up there. Okay, so aluminum is 1.5 and oxygen is 3.5. Equals 2.0. All right, the general rule, if you recall, stated that if it is above a 2.0 or around there, 1.5, 1.8 to 2.0 or higher, is going to be ionic, which both of these are ionic. So we're going to change the color of ionic just so that we can see it to red. Okay, so these are ionic. So we'll have our own little key. See, these are ionic because they're a metal and a non-metal, just like we had said. All right. Non-polar covalent and polar covalent. Now, polar covalent is supposed to give you a difference greater than 0.5. So I'm going to make this one blue and non-polar, I'm going to make them green, okay? So we have them, all different colors. Hopefully you can tell the difference between them all. All right, so based on this, NO2 would be hard to tell, yes? Because it can be either or. So the other way to tell whether it's a non-polar or a polar is to look at their Lewis structure. And to do that, we need the math for it. So let's do that math for the NO2. So you got one nitrogen. Let me put it up higher so I can actually see it. Okay, yeah. one nitrogen, so nitrogen, you have 1 times, times 5, right? And then you've got, oh, you have 2 of them. That's supposed to be a capital N, but that's all right. All right, oxygen, you have 2 of them. And they're in group 6. So that equals 12. So you have, interesting. Okay, I should put supposed to be NO2 negative, I believe. So let's put NO2 negative. I think the negative went away. All right, so let's add one more because it's a negative, right? So it's 17 plus 1 gives me 18. All right, so that's that. So when we are looking at doing the structure, we got a nitrogen, 2 oxygens. We used 4, so we got a total of 14 left. So we got to put the little dots. I'm gonna need dots, actual dots. So here we go. 1, nope, that's not working. It is not letting me put dots. Okay, so let's just make it thicker then. That'll probably work. 1, 2, 2. Already counted them, sorry about that. So we've got 14, right? So 6 on each one of the oxygens and 2 on the nitrogen. But nitrogen is going, hey, I'm not an exception. I need an extra electron myself. Therefore, you move that one to the middle. And there you go. That is your NO2 negative 1. So this is actually your Lewis structure right there. But the most important part is that it has a lone pair. What we couldn't tell before, right, because it's so close to being a yes or a no, is that it looks like a non-polar. It could be a polar. We didn't know. But in this case, it is polar because we do have the lone pairs. So we can clear all that and go back and give an answer to that one, which is that we need to put it in blue. So this is polar covalent, even though the delta electronegativity tells me it's okay. Now, as far as we know, water is polar covalent. We've talked about how incredibly hydrogen bonded it is, and the only thing that it's not going to be is, nonpolar. Now, carbon disulfide in this case is going to be, you have to do the math, but it's actually going to be carbon double bonded to S's. So nonpolar. So in this case, we have green. Now, boron trifluoride, we know boron is one of the exceptions, so it's not going to have any lone pairs. So again, green. See, and there you go. Those are your nonpolar covalent and your polar covalent and your ionic. Okay, 2 of each. Now, if you were to do the delta electronegativities for BF3, one is 2 and the other one's 4, it gives you 2. So it makes it look like it's polar, but it's not. And that's why you have to do the other type of assessment. You have to have, well, number one, the ionic is easy, even if you don't do the delta electronegativity because it's a metal and a non-metal, which both of those are, A and E are. The polar covalent, it has to have lone pairs. And so when you're looking at something that's as symmetrical as carbon and sulfur, you know that sulfur needs 2 bonds, carbon needs 4, And you do the math, you know there's not going to be any leftovers. And boron trifluoride happens to be nonpolar because of its symmetry. Okay, and that's all. All right, so for this next question, it's asking us, why is a compound that is covalent have a distinct odor, but an ionic one does not? Remember, one characteristic of ionic compounds is that they have a very high melting and boiling point, right? So if it's just at room temperature, you're not going to smell it. Whereas a covalent compound, like alcohol, for example, is very volatile, which means it readily changes into a gas at room temperature, which means it's a lower boiling point. Therefore, you can smell it. And in order for you to smell something, it has to actually become a gas so that your nose can, inhale it. Therefore, there's your answer. I'm not writing all of that, but you can. All right. And okay. So remember, this is all a matter of looking at one thing only. Number one is, what is our Lewis, what is our, not Lewis, sorry. What is our group number? Our group number for this one is 4, yes? 4A. So the answer is 4 for neon. And you notice I'm skipping the ones that aren't positive, that are positive or negative. So right now we're just doing the ones that aren't. Well, that one's 8, right? Then you've got nitrogen. Nitrogen is 5 because it is in group 5. We know all of these. Those are easy. Okay, so since we know those, let me just make the color correct so that you know that this is what we're talking about. All right, now, potassium would have 1, yes? But then it lost that 1. So the amount of valence electrons, which means the outer shell, is not 8. Why is it 8? Because 8 is where the next layer is. You have 8 electrons. Okay, they're listening to me. You have 8 electrons on that shell. And that's what we know. Oxygen has 6 normally. And it gained 2, so it also has 8. Hydrogen, in this case, gained 1, yes? So it has 2, because it normally only has 1. Look at that thing over here. I just put it right here and it went away. Now that I'm putting 2 on here, it won't let me. Oh, this thing's annoying. It has 2. And that is all it can have because it is only 1 level. Remember, 1 electron level in hydrogen. And that electron level can only hold 2 because it's your first one. All right. Now, why are some solvents polar and some non-polar? Okay. Because of some solvents are polar because they have their Lewis structures have extra electrons, or they're asymmetrical, or whatever you want to call it. There's also a dipole moment that exists between the bonds, right? So that's because of their polarity. All right, so which one would you use to dissolve salt? The answer is the polar. Why? Because salt is ionic. Ions are charged. Charges, attract charges, right? So positive attracts negative and negative attracts positive. So if you have something that's partially polar like water, salt will dissolve beautifully in there. But if you put it on something non-polar like oil, it would not dissolve at all. All right. Drawing Lewis structures for these is probably the easiest thing we'll do today. All you got to do is which group are they in? They're in group 4. So 1, 2. What on earth? What? Okay, that is so not what I want. 1. There we go. I want it permanent. That one was like moving off. All right. Helium, since it is in group 2, but it is also a noble gas, that means its one level is full. We put the 2 together. Phosphorus is in group 5, so we go around. Remember, this is 1 on each side, and then we double. So that's a double. It's supposed to be a double. That looks terrible. Let me try it a little bit better. There we go. That's better. Nitrogen, the same. It's in the same group. So it's 5. 1, 2, 3, 4, and 5. Aluminum is in group 3. So it only has 3. 1, 2, 3. And they all can form bonds. Sulfur is in group 6. So 1, 2, 3, 4, 5, 6. You see that? And that's how you do the Lewis structures for those. All right. I think we are out of time right now. So we are going to continue next time. Just remind me where we were, please. And that's the naming. I know with you guys, with the other class, I ended up somewhere else, but with you, it's the naming. So 13 for you next time. Hopefully I'll see you Wednesday. It's our last day. And when we do that, we will be in person again. And if you can't, like I know you guys have tests or whatever, and sometimes they last longer. So if you cannot come to the 11 o'clock session, there's a 9:30 session on Wednesday also. And there's also going to be another session on Thursday. Well, no, maybe not. It just depends. I might do it online for the Thursday people. Oh, you know what? Let me stop. Yeah, for the Thursday people, and that would be at 9:30. Okay?
Okay.
All right. So that's all I needed to